So we're going to work with absolute value inequalities today. But first, let's just talk a little bit about this first example where absolute value of x is greater than or equal to 7. So we know that the absolute value, if the value inside the absolute value symbol is a negative number, then it's going to come out to be a positive. And if it's a positive number, it's still going to come out to be a positive because the definition of absolute value is the distance away from 0 in either direction. So if the absolute value of x has to be greater than 7, then we can actually say that negative 7 is a value of x, and the positive 7 could also be a value of x. Well, we could say negative 8 can be a value of x, and 8 can be a value of x. Well, negative 9 could be a value of x, and positive 9 can be a value of x. And we can just continue to fill in the number line because all of these values of x allow the absolute value of x to be greater than 7. So when we graph this using our notation for graphing, we would actually say we would put a closed circle, a closed circle on 7 right here. So we have a closed circle with the arrow pointing less than, and over here a closed circle with the arrow pointing to positive infinity to the right. So all of those values of x are legitimate values that satisfy this statement, that make the statement true. So in interval notation, we've already learned this. This is just an or statement. So notice, and I want you to take note of that this particular example creates an or situation. We have negative infinity, comma, negative 7, and it's included union positive 7, comma, positive infinity is the interval notation. So all of those values, all of these values here, on to negative infinity, and all of these values onto positive infinity, satisfy the fact that x, the absolute value of x, that is, can be greater than or equal to 7. So in this next example, we'll see a slightly different situation because now we have the absolute value of x is less than or equal to 4. Okay, so now let's think of values of x that would make this statement true. So in that case, we would have values such as 3. Or negative 3, or negative 2, positive 2, negative 1, positive 1, 0. So all of those values, and of course negative 4 and 4 because it says equal to, so all of those values actually make that statement true. So in that case, we would write the inequality, we would write the inequality so that we would have a closed circle at negative 4, and all of the values between negative 4 and 4 are valid values of x. Because if we were to put a negative 5 in the inequality, absolute value of negative 5 is not less than or equal to 4, because the absolute value of negative 5 is 5, and 5 is not less than or equal to 4. So that is not a true statement. And even if we put a positive 5 in there, the absolute value of positive 5 is still not a true statement. So therefore, we can conclude that the only possible solutions to this inequality are these right here, from negative 4 to positive 4. So we'll write that in interval notation. And so we have negative 4 comma 4, both with the square brackets because we have an equal to. Now let's notice here that we have an and situation. So in the example just above we had an or, This one we have an and those are both very important pieces of information. So you need to note that absolute value inequalities are compound inequalities also. So let's see how we can solve these. So in this section of the foldable, they identify four steps for solving either case 1 or case 2. And actually, you use the same methods regardless. All right, so we first want to isolate the absolute value expression, and then we're going to create two different cases. So we need to create a case for the positive value and a case for the negative value, and we'll see both of those, and then we're just going to solve both of those two different cases, graph the solution, and write your answer in interval notation. All right, so let's start with problem 1. So this first could start off a little confusing, so just bear with me as we go along. So we first need to isolate the absolute value. Well, in this case, the absolute value is isolated. It's the only thing on the left-hand side. So then the next thing we have to do is create the two cases. So remember that absolute value, the value inside the absolute value sign, can be positive or it can be negative of the evaluated value. So that means x plus 6 can be a positive 7, or x plus 6 can be a negative 7. Now with inequalities, we have to worry about the inequality sign. So we always, on our positive numbers, we always maintain the inequality that's been provided in the problem. So x plus 6 can be greater than 7. But when we're looking at the other side, the negative value, we have to reverse the inequality sign. So in this case, x plus 6 is less than negative 7. And as we get work in the problem, you'll notice why that is. So this is an example of the type 1 above. So this is a greater than, which is going to produce an or statement. Because remember, we're going further and further and further away towards the infinities because we're going greater than 7 away from that center point. So as we solve these two separate equations, we're just going to subtract 6 from this one, so we have x is greater than 1. Over on the second one, we're going to subtract 6, and we'll have x is less than negative 13. And so when we graph those, it's going to be an open circle at negative 13, and x is less than that. And with x greater than 1, we have an open circle at 1, and we're pointing to the positive infinity. So notice we have an or situation here, and we'd write the interval notation appropriate for the graph. So we have negative infinity, comma, negative 13, and it takes a parenthesis because it's not included, union, parenthesis 1, comma, positive infinity. Okay, so now why do we have an or? Well, we have an or because we're using greater than. Our absolute value, whatever is in here, is going to come out to be greater than 7. So this could be a negative 9 in here, and when it comes out, it could be 7. It will be greater than 7. If it were negative 10 in here, it would come out to be greater than negative 7. And that's all we want to make sure of, is that whatever is inside here is greater than 7. So the this value in here can be greater than 7, which is what we've said here, or that value in there would have to be less than negative 7, because if we were to say that, let's just say x equals negative 14. So negative 14 plus 6, the absolute value of that, let's do this. So negative 14 plus 6 gives us negative 8, absolute value of negative 8. When we evaluate absolute value of negative 8, we get 8. And 8 is indeed greater than 7. Okay, so we have to make sure that we can go, we're increasing the value in the negative direction as well as increasing the value in the positive direction so that it's always greater than 7. Let's try number 2. So again, this one is isolated already. The absolute value is all by itself on the left-hand side. So now we're just going to set up our two cases. So we have 2v minus 3 is less than 19. Okay, so now when we deal with the negative value, we're going to reverse the inequality sign. So for the second case, we have 2v minus 3 is greater than negative 19. And so if you recall up in the examples, when we had the less than sign, we ended up with an and situation. And that's what this will end up being as well. So let's continue to solve and we'll see that. So we're going to solve this first case and add 3 to it. And when we add 3 to it, we have 2v is less than 22. Divide by 2 on both sides. We have v is less than 11. On the second case, we add 3 to both sides, and we have 2v is greater than negative 16. Divide by 2, and we have v is greater than negative 8. Okay, so let's graph those. So we'll graph this first one. V is less than 11. So here's 11. We're going to put an open circle, and we're going to go less than. So the arrow is going to go in that direction. Over here, we have V is greater than negative 8. Open circle, greater than is going in that direction. And so recognize that because we have to satisfy all of those conditions, we end up with an and situation. So we have our lower limit and our upper limit. So in interval notation, just as we saw before, we put our lowest number to the left, so that's negative 8. And our highest value, which is 11, and because they're not equal to, we put it in parentheses. Okay, on number 3 and number 4, I will solve them, but I want you to try it first and then restart the video and see if you got the right cases set up. So here are the two cases. Now go forward and solve them by yourself and then resume the video. So here's the solutions to the two different cases. Notice I added 5 in both cases, and then I also had to multiply by 3 to undo the division by 3. And so we have k is greater than or equal to 18, and k is less than or equal to 12. So we'll graph that and write the interval notation. And there's the graph and the interval notation, and we'll work the problem number 4 the same way. So here are the two cases. So remember, we keep the inequality the same way when we're dealing with the positive answer, but we reverse the inequality when we're dealing with the negative answer. So now solve both of those and come back and see the video to see if you got it correct. So here's all the work, and I just want to point out to you that in this particular case, on both situations, we had to divide by a negative 4, which meant that we reversed the inequality sign. So here we had less than or equal to, then it switched to greater than or equal to. Over here it was greater than or equal to, and it reversed to less than or equal to. And that's just because we divided by the negative 4, or a negative number. So now let's graph it and write interval notation and check your work with the video. Alright, so there's the graph and the interval notation. So I'm going to work a few more problems, but it'll be on a separate video so that you can see those problems and get a little bit better familiarity with how to work them. Good luck.